In lecture 24, we talked about both intrinsic and extrinsic semiconductors. This is a rather long lecture. We talked about electron and hole concentrations in semiconductors in general, the quantitative relationships, and then we talked about the intrinsic carrier concentration and Fermi energy. And then we moved on to talk about extrinsic semiconductors. We talked about what are the donors and acceptors, and then the N-type, P-type, the carrier concentrations, Fermi energy locations in these extrinsic semiconductors. Finally, we talk about compensation doping. So the first student learning outcome, this is really trying to finish up the intrinsic semiconductor lecture in 23, is to relate the electron hole concentration in a semiconductor to the Fermi energy position and also perform the quantitative calculations. So we have this electron concentration expression, and we can obtain a similar expression for the hole concentrations, which relate to the effective density of states in the valence band and the exponential factor of a state at the valence band edge occupied by a hole state, which is basically not occupied by electrons. Okay, so in both cases, you can write them down as a effective density of states multiplied by e to the minus delta E over KT. And this delta E is EC minus EF for electrons and EF minus EV for the hole. So basically, the Fermi energy location will have a critical influence on the carrier concentration in the bands. And obviously, the effective density of states also affect the carrier concentration in the bands. So in the same semiconductor, when we move the Fermi energy up, that means closer to the conduction band edge, we will have a exponentially increasing electron concentration and exponentially decreasing hole concentration. Okay, and obviously when EF goes down, that means closer to the valence band edge, we will increase the hole concentration and at the same time reduce the electron concentration. But if you look at the product of the electron hole concentrations, it comes out to be a constant and it's independent of where the Fermi energy is. So that's called a mass action law. It depends on the temperature, obviously, but it doesn't depend on the Fermi energy location. So the amount of increase in the in the electron concentration and the amount of decrease in the hole concentration ratio-wise will be the same. So the second student learning outcome is to predict the carrier concentrations and Fermi energy location in an intrinsic semiconductor. Okay, so we have the electron hole concentration product being a constant, independent of, well, constant means independent of the Fermi energy location. It does depend on the temperature and band gap, all those other things. So for intrinsic semiconductor with no impurities, then the thermal generation leads to electrons in the conduction band and holes in the valence band. And that means these two quantities are the same. We define them as N sub I. We call that intrinsic carrier concentration. So this product is really just Ni squared. So that means Ni is just a square root of NCMV times the square root of that exponential factor, which becomes e to the minus Eg over 2 KT. So you see that this intrinsic carrier concentration does depend on effective density of states, which has a slight temperature dependence, but more importantly, it depends on the band gap and temperature in this exponential factor. When you have the intrinsic carrier concentration, plug it back into either of those two equations, you can obtain the Fermi level location for the intrinsic semiconductors. This is going to be given by this expression. And because the NCMV are not going to be extremely different, and also it's going to be multiplied by this KT, which is very small compared to the band gap. So for the most part, it's going to be dictated by this half midpoint between ECEV. So it's sort of saying that the intrinsic Fermi level is going to be about at the mid-gap location for these intrinsic semiconductors. We can have extrinsic materials. That means we provide doping. We dope impurities into these semiconductors. So the concept here is that you need to know what constitutes a donor and what constitutes an acceptor in a semiconductor, and also qualitatively explain how this doping will affect the carrier concentrations, Fermi energy locations, and conductivity, and so on. So for doping, it's a process of incorporating impurities, and we're mostly talking about substitutional impurities. So for the impurities, we can have two different kinds, donors and acceptors. For the donors, these are the atoms that have more valence electron than the atom that you take out. So if in a silicon has 4 valence electrons, putting arsenic, which has 5 valence electrons, you can have extra valence electron, which can be donated to the conduction band and then generate extra excess electrons in the system. When you replace a group 4 element like silicon with a group 3 atom, then it doesn't have as many valence electrons, so you need to grab electrons somewhere else to fill the four bonds with the nearest neighbor that give you holes somewhere in the system. Then we call them acceptors. So in the doped semiconductor, the donor impurities will contribute electrons to the conduction band, and these energy levels of the donor states are going to be relatively close to the conduction band edge, only within 1 or 2 kT. And for accepting impurities, the electronic states are going to be relatively close to the valence band edge. That's why they can have a chance to donate holes into the valence band. As a result, when we incorporate donors, we are going to increase the electron concentration much greater than the hole concentration. So we call these electrons are the majority carriers, holes are the minority carriers in this system. And that's why we have so-called N-type semiconductor. And as a result, the Fermi energy location is going to be above the intrinsic Fermi level. It's going to be closer to the conduction band edge. On the other hand, when we incorporate the acceptors into the systems, we have a so-called P-type semiconductor. The hole concentration are going to be much greater than the electron concentration. So in this case, we call these holes are the majority carriers and electrons are the minority carriers. And then the Fermi energy location will be closer to the valence band edge and below the intrinsic Fermi energy. So the next student learning outcome is to perform a quantitative calculation of the carrier concentrations, Fermi energy locations, and conductivity for these doped semiconductors at room temperature. So the assumption here is that in intrinsic semiconductor, we obviously have electron hole concentration being the same, and the Fermi energy location is roughly at mid-gap locations. But for the doped semiconductor at room temperature, we assume that all impurities are ionized. Okay, so we have electron concentration being much greater than the hole concentration, and Fermi energy location is above the intrinsic Fermi level. And for the P-type, again, if you assume all the impurities are ionized at room temperature, then the hole concentration is going to be much greater than the electron concentration. Fermi energy location is going to be in the lower half of the band gap. But quantitatively, how do you calculate the carrier concentration? Well, in this case, when all the impurities are ionized, then the majority carrier concentrations is going to be dictated by the doping concentration. So in the N-type case, the donor concentration gives you the electron concentration, and then the minority carrier concentration, well, once we know the majority carrier concentration, we know the product N and P is Ni squared. So once you know N, you can calculate P. Okay, and then once you have those carrier concentration, you can also determine where the Fermi level is using these expressions that derive from those two equations. So for the P-type semiconductor, again, you assume all the impurities are ionized at room temperature. So the hole concentration, which are the majority carrier concentrations now, it will be dictated by the acceptor doping concentration, and then the electron concentration will be given by Ni squared over P. And then you can also determine the Fermi energy location, which is related to the doping concentration or the hole concentration in this case. Okay, and then you can also rewrite the NMP with respect to the Ni by looking at the Fermi level location. How much is it shifted from the intrinsic Fermi level? And so that you do variations of how you calculate the Fermi energy location. So in that case, you're referring the Fermi energy location to the intrinsic level, or you can refer them to the EC/EV. Remember, for the semiconductors, anytime you talk about the Fermi energy, we're actually talking about the location of the Fermi energy, Fermi level. So you have to specify a reference. In general, as EF moves up, we have N going up exponentially, and P goes down exponentially. So the last student learning outcome is to explain what is compensation doping and how it affects carrier concentrations. We have these two rules set up with only donors or only acceptors. We get the N-type or P-type semiconductors. But what if we have both type of impurities, intentionally or unintentionally? Then we can no longer just say that electron concentration is dictated by the donor concentration and holes are given by the acceptor concentration, because in that case, the product may be much greater than Ni squared. So in that case, we're going to have excess carriers, and as we talked about earlier, we're going to have recombination. So this is actually called compensation doping, and the compensation comes in the fact that electrons contributed by the donor may not go into the conduction band all the time. Rather, they will have to fill the empty states on the acceptor first. Okay, and then you have to see which ones got more. If we have more donors than acceptors, then we're going to fill all the acceptor states with electrons from the donors, and then we have some donors left behind. And these donors now they are going to contribute electrons to the conduction band. So in that case, the electron concentration is going to be given by the difference between the donor and acceptor concentrations. But if we have more acceptors than donors, then we're going to have a p-type semiconductor, and then the whole concentration is going to be given by the difference between the acceptor and donor doping concentrations. So this composition doping will occur just because that we are going to have both type of impurities unintentionally all the time, but sometimes you also do the intentional doping with incorporating both type of impurities. So this is the end of lecture 24 review.